Good morning, good afternoon, good evening, wherever you are. My name is 𝘕𝘊𝘄𝗎𝗓 and I am the CEO for Carbon Solutions LLC. Today, I'm going to talk about our vision or our concept called Gigatonne One. The grand challenge, the time for CCS is now. We know this. We know that CCS is part of every major clean energy pathway. And we know in the coming decades, by the end of the decade, we need to be capturing, transporting and storing hundreds of millions or billions of tons of CO2 worldwide. We know that there's over 100 countries either have or considering a price on carbon or credits. We have 45Q tax credits in the US. We know China has the emission trading scheme coming up where CCS will kick in by 2030. We know that carbon as a resource utilization is coming about. Carbon economies where there's widespread availability of low-cost CO2 can be used for a whole range of materials. So we know the time for CCS is now. We have to make this happen. There's energy transitions all over the world. We need to be thinking about CCS infrastructure on a massive scale. And that's where the concept Gigatonne One comes in. It's all about getting to the billion-ton scale of CCS. And we know to get there, we need to develop a roadmap. How do we get to that gigaton scale CCS over space and time? Things change over time. And ultimately, we know there's going to be hundreds and hundreds of pathways that we could get to gigaton scale within a country like the US or within continents across the globe. And these hundreds of pathways, we know that there's multiple different pathways based on technology and CO2 incentives and policy and regulation and industry reducing carbon footprint and the price of CO2 and the changes in oil and financing and economics and so on. And if we threw in uncertainty, we know there's going to be thousands of pathways of how we could or should get to gigaton scale CCS. That's what this vision is all about. And how are we going to do that? The way we think we can do it at Carbon Solutions and with our partners in the SimCCS community is a tool called SimCCS Pro, which you might have heard of already. And that's what I'm going to talk about today, how SimCCS Pro can meet our gigaton scale vision. So I've already talked about the why, the drivers to make this happen. We're talking about SimCCS Pro. It's a decision support software that can help you deploy CCS infrastructure over space and over time. It uses supercomputing. And if you look at the bottom left, you can see the web links to learn out more. You can see there's over 100 people who've worked with us on this. We have a couple of dozen publications and thousands of citations. We are the leading this is the leading tool set for understanding regional and even local CCS infrastructure. The top right shows an old figure of what CCS infrastructure might look like in the southeast of the United States. This has changed very much now, but it shows you the red circles where we're capturing CO2, the blue circles where we're storing CO2. We see gray lines, which is the candidate network, places we could build pipelines, and the green lines is a SimCCS solution of showing you not just where the pipelines are, but how big these pipelines should be. And now I'm going to flick to the animation that just shows you, this was, we did some work with Southern Company. We looked at capturing up to 100 million tons of CO2 from the coal-fired power fleet. And what would that look like? And we can look at the economics and the engineering of the pipeline network, the costs and the pipeline diameters and so on. That's what SimCCS Pro does. Here's an overview from the open source version of SimCCS that won an R&D 100 award of what the workflow looks like. We have these 4 stages: map, build, solve, analyze. The right-hand side details what they are, but basically the map is bringing in raw data. The build is the unique way to build that data into a format that SimCCS can use. The solve is our unique optimization engine, which is either an optimal linear program that it solves or a heuristic, and this can be done on your desktop. It can be done with high performance computing. And then finally analyze. That's what we want to do with this. We've run all of these models. We can come out with hundreds of different CCS solutions. How do we do that analysis? And here's just a schematic of the data and all the information that goes into a single SimCCS run. The hexagon at the middle is the SimCCS decision optimization engine that simultaneously looks at capturing, transporting, storing CO2. At the bottom, you see some of the kind of things that you can do with SimCCS. But really what I'm going to talk about today is the capture, the transport, and the storage model that go into SimCCS. They can be used as standalone tools, very much on their own, or they can be used to parameterize and CCS. So the capture, transport, and storage tools you hear about today, Nicole Pro, COSMAP Pro, and Scott Pro, which we had a previous, we have a later talk on at this conference. So let's start with the capture database called Nicole Pro, and this is what allows us to understand what commercial scale CO2 capture could look like. We're doing this just for the US right now. We fuse data from multiple different data sources. We fuse in capture economics and CO2 stream information from 1 or 2 dozen different literature sources, and we build this database on the fly. So what you're looking at right now, every time you rebuild this database, it takes a few seconds. You get a new version of what it might look like. So one outcome you get from Nicole Pro is a geodatabase showing you where and when you have these CO2 emissions and their costs. A second output you get is CO2 supply curve, a classic economic supply curve here. CO2 from cheapest to most expensive from left to right, and then you can see the quantities on the y-axis. For the country or any region, we can go in and show what the capture opportunities look like. Similar like a coal plant, typically there's only one stream of CO2. For something like ethanol production, the bright green bars you're looking at, there's at least 2 streams of CO2, the kind of fermentation, CO2 emissions, and then the combustion source. So we can really break it down into that data, into that detail with the most advanced economics. And then the third thing that really, given the geodatabase and the supply curve, we can do a market analysis of understanding what CO2 capture opportunities are out there. So that's a really quick overview of the Nicole Pro tool. The second part is for transport, and we have COSMAP Pro, and it's the most advanced tool we believe out there for routing pipelines. It routes it down using data down to the 30-meter grid level, so very fine resolution, and it merges in geographic data covering population and land use and land cover, rights of way, including roads and transmission lines and pipelines, and it builds this all together in a complex nonlinear way to give us a routing surface to understand how we might route pipelines, and users can change all those weights to kind of impact the routing, and then a cost surface that assigns these advanced costs to the routing. And so this is a really good way of understanding where pipelines could or should be routed, and we can understand if you want to avoid a county or Native American land or population, you can change all these weights, get down to that really fine scale pipeline routing. At the national scale, we typically use 1,000 meters. For a very local project, we'll be down at the 30-meter level. And here's a quick overview of what it looked like for a study we did with the Great Plains Institute looking at CO2 transport in Texas. Red dots is the capture, blue dots is the storage, and those white lines are the low cost potential likely routes for pipelines. So that's what we can do with COSMAP Pro. Scott Pro, which had a full talk about covering all the details, is a new advanced tool for understanding dynamic CO2 injection, dynamic plume evolution, and coupling this to sequestration economics, and nobody else does this. It's a tool that can do thousands. It does up to 10,000 simulations a second, whereas a typical full physics code like FEHM would take 5 hours for a single simulation. We can do 5,000 a second. It's all Excel based. Anybody can just, you can just use this on any PC or Mac. You don't have to install anything. And it really gets us to understand what CO2 sequestration might look like. So we can look at sensitivity analysis, which is what these figures are I'm showing here on the right-hand side. And that comes from a recent paper in Energy Environmental Science. And so we can understand these new and novel sequestration science that we didn't understand. In addition to sensitivity analysis, we can do uncertainty analysis. But the key is we're not doing volumetric assessments here. We've moved way beyond that. This is dynamic injection and storage. Beyond the uncertainty and sensitivity, I should just highlight this. This is an example where we looked at increasing depth. What happens when you look at deeper and deeper formations? The literature before we looked at this suggested favorable CO2 properties as you go deeper lead to favorable CO2 sequestration. What we found out is, in this case, if you go deeper and deeper, if you limit injection to a maximum of 1 million tons a year, you get this inflection point. That's what these red circles are. Once you reach 1 million tons a year, you can't inject any more CO2 than that. The well bore won't allow it. And actually what you find out when you look at the bottom right-hand corner, your costs actually go up. So whereas the science generally believed that deeper was better, this just isn't true. And this is one of the things that we found out in this paper. And there's a range of other novel and important things we found out. And we couldn't do this. We couldn't understand this new sequestration science without Scott. But then the other part of Scott is, and this is what's really important for Gigatonne One, is we can do regional analysis. The top left figure, we're looking at Scott applied to the Illinois basin, where the height of each bar is proportional to storage capacity, and the color is proportional to cost. And then the bottom right is just showing what it kind of the cost could like across the nation. But now that we have this tool and we have the Scott geologic database for the country, we're able for the US to look at, well, what does it look like if we needed to sequester hundreds of millions or billions of tons of CO2 each year? We have the tool that's able to do that, and nobody else has this tool. So we haven't done Gigatonne One yet. It's a vision, it's a concept, and we're really pushing it. We think it's the way to go. But here's an example of some work with the Great Plains Institute, looking at what national scale CCS could look like. So we're getting closer and closer. We can do Gigatonne One now. We just need the project to be able to do that. And I wanted to show an example of how we're already basically doing analysis of this. So really quickly, to wrap up the kind of the take-home message, just to repeat what I've talked about, I'm showing the R&D 100 award, the 2 awards on the right-hand side. But CCS is part of every major clean energy pathway. We know what we need to do and the scale we need to do it. And now we need to develop roadmaps. How do we get there? There are tens, hundreds, thousands of pathways to get to gigaton scale CCS. How do we do that? And that's what Gigatonne One is all about. And I'll finish up by saying, we can do this now for the very first time. We have the people and the expertise. We have the need to do this. Absolutely, we have the need. And for the very first time, we have the SimCCS Pro tool sets. We have Nicole Pro, we have CostMap Pro, we have Scott Pro. We can do this. So thank you. Again, my name is Richard Middleton. I'm the CEO of Carbon Solutions LLC. You can go visit our preliminary website and find out more information about what we're up to. Thank you.